how would a smart high school student put this on a computer? I say high school because it really requires nothing than Euclidean geometry. And sweeter still, we'll be able to write analytic formulas for Jacobians, and they'll be very intuitive. So there's one system in which, and we'll be even able to compute stability of periodic orbits analytically for a few orbits. And I'm actually very proud of this because I had a collaborator that produced 1,000 orbits, and I analytically computed the third one, and he was wrong at 1% level. Now, in this class, we expect you to be good to machine precision. This is deterministic chaos. So he had to shave his head in shame. No, he didn't, because the modern German has no pride, but he fixed his program and everything works. So, it's wonderful to have kind of analytic thing at hand when you can have it. Unfortunately, it's so rare, but this is one case we can do it. We'll put few disks in a plane, and we'll be so lazy we'll only use 3. If you use infinitely many, that's called Lorentz gas, and it's a very useful thing in statistical mechanics. If it's 3, it's just, when you have a pinball machine and you send balls from here, then at the top there are 3 disks, and they're doing chaos for you, randomizing on dynamics. And in the movie I'll put beautiful paintings of these pinball machines. If you don't believe me, that's what they look like. And we'll take very small point, infinitesimal. Turns out it's not crucial, but the only thing that matters is a circular elastic scattering, and it cannot gain angular momentum. So the only energy is just in the motion. And we'll get started someplace. And what this thing will do is, like in any pinball game, it'll bounce maybe a few times. If I'm very good, then it'll fall apart. It'll fly out. And I'll use this to explain everything about how you think about chaotic dynamics. So this is a typical pinball game. Now, if you're a very good player, you might aim it in such a way it bounces a few more times. But it pretty soon turns out that if you want to control 10 bounces in the future, you have to have your initial condition specified to 1 Fermi or something, to subnuclear distances. So it's not going to work unless you cheat. That's called control theory. You can do this. As the pinball wizards do, they actually move the table. We're not allowed to cheat. What I want to describe now is how I depart from here and how I depart from the next disk. And that turns is kind of very elementary geometry. So here am I on one disk. So I shoot out, and I do this at a position s minus 1 time, and I'm here on the perimeter. This is s. And I do this with uniform velocity, a vector. It's a unit vector. What it does reflects here, and to see how it reflects, I have to write the line that connects the center of the disk at time n. That's a symmetry line. And the specular, we have the same angle, and that's Vn plus 1. And it hits the disk at the point. So now I want to explain how you compute this position and this velocity if you are given your starting point and the center of the next disk. So usually the billiard is described, you just specify coordinates of the disk and their radii, and that's how you specify the billiard, the pinball kind of billiard, like this one. The beauty of this simple problem is this is specified, a line is a linear problem and a circle is quadratic problem. And it turns out to evaluate this point, we'll only have to take square root once, and that's all. Everything is elementary. You don't even have to compute the sine or cosine or anything with trigonometric functions. And if you look at competing books, they're full of sines of cosines, etc. So they never tell you that you don't act. If I know where I know where the center of next vector, I'll call it D. Now, what I also know is, I know the vector that's normal to this line. And this vector has a name that you must have seen. It's called impact parameter. So in scattering problems in electromagnetism and quantum mechanics, this tells you how big the scatterer is. Usually it's some potential, but here is a very literal quantity. The disk has a radius, and if your line goes outside, you don't see there is a disk. In four-dimensional phase space, this is a two-dimensional configuration vector n-1. In our Poincare section, it's specified by s n-1. And this is the next point in four dimensions. So what does this has to satisfy? It has to satisfy that x n minus the center of the nth disk. First thing we have to figure out, am I going to hit the disk? I'll rotate at the velocity at n-1, and 90 degrees in a plane is very simple. You just exchange x and y. So this is by construction normal to that. I can compute the parameter distance as bn equals, so the distance along here, as a product of this thing times u n-1. This by construction is a unit vector because v was a unit vector. Now, everything I write might be wrong, right? So I expect you to keep me honest. Collision happens if c square, which is the difference of the radius minus parameter, or you require that bn over an is smaller than equal than 1. So when you write your program, what do? You write a routine which computes the intersection of this line and the circle. Then you check whether b computed, from the information that you already have. You know the distance to the center and next center, and you know this 90-degree rotated velocity. You just have to check whether it's smaller or equal to 1. If it's smaller to 1, you have a collision, so you continue. If it's larger than 1, you don't have a collision, so you keep checking whether your line is intersecting any of the other disks. If you have only 3 disks in the plane, you have to check only 2 disks. And if it doesn't intersect either one, then it's run off the table. You'll never come back. So it's very quick as a computation is. The next step is we hit the disk. What do we do then? I find out that b is smaller than 0. I'm hitting the disk. Then I have to compute, the time of flight, because in dynamics I care about when will I arrive. Is dn minus 1. Now you multiply it by velocity, not by turnaround velocity. That gives me this whole length. Minus c of n, and c of n is the positive root of a square minus b square n. So this is the only nonlinear thing. So to find time of flight, you need the root, and you might wonder what is the minus sign. In some cases, like in quantum mechanics, you might actually care about minus sign. Minus sign tells you what the far away intersection is. So the line intersects twice. You care about the first intersection. That tells me I have started here, I ended there. Now I have to find out the momentum. So this gave me the position, but I need the momentum. We have this axis, this an vector, the unit vector pointing out here because I need this unit vector in my formula, so I need n here, normal to the circle right there. It points radially, so it's very easy. And it's 1 over an to make it unit, radius of the disk. And then it's b, and this is the impact parameter. I use my specular law to describe the reflection. What happens at the reflection is I can define the endpoint of this to be, x prime. By the reflection, the position doesn't change, so that's the same. See, what didn't change here is the velocity didn't change. I get instantaneous acceleration. So I get a delta function acceleration that, because this is a infinite wall, which in instant in time changes my momentum by the specular reflection. Because it's a mirror, you get a minus sign here. You know, if you hit it directly, it just come back. So that's this minus sign. And but you have to now also take care of the wall normal component. So that's it. So you write a little routine, exactly what I did here. And what it does is it gives you the next point in your full phase space coordinate and next velocity in full phase space coordinates. If you want to go back to our Poincare section, is some arbitrary coordinate, you know, because you have to set z equals how you move around the parameter, so it's the same as the angle. To compute s, you have to take arc sine. And this one you know because you know the p parallel. The dynamics is now split in two parts. The free flight part, followed by reflection, and that's associated with, at time n, there's a transformation that puts me from here to there, which is a linear operation. So this is my map, 4-dimensional vector n plus 1 from 4-dimensional vector xn. And at the same time, you have the dynamics in the Poincare map because you know exactly where you are at every iteration and what the parallel velocity is. So all it requires is you go forward, you see where it intersect the circle, you compute the intersection, and then you reflect your line along this line and you keep going. And you need one square root because circle is quadratic.